Integration often feels like an entirely new language, but it doesn't require learning a new branch of mathematics from scratch. Integration is simply the exact reverse process of differentiation. We are literally running the math backward. If you know how to derive, you already have the core logic for this chapter. This means most of the tools you need are already familiar. Mastery here depends on shifting your focus from learning new rules to recognizing existing patterns in reverse. However, reversing the math creates a specific gap in the information. This is why every indefinite integral ends with a plus c. When we differentiate, we measure slope, eliminating standalone constants. Notice how these parallel curves, despite different heights, share the exact same slope. Because the derivative is identical, we don't know the original vertical position. C represents that unknown height. When you solve an indefinite integral, you aren't defining a single line, but an entire family of potential mathematical paths. Basic formulas only work for simple equations. To handle more complex expressions, we need a method that simplifies the algebra before we start the integration. For substitution, you identify a base function and its derivative. Here, x squared and 2x sit right next to each other. Replacing this linked pair with a placeholder variable condenses the entire expression into a standard formula you can solve in one step. This method clears away the algebraic noise, allowing you to solve the core calculus without getting lost in the variables. Other problems involve two completely different types of functions multiplied together, like an algebraic term and an exponential term. In these cases, there is no shared derivative, so substitution won't work. For these, we use integration by parts. The challenge is deciding which function to integrate first. Picking the wrong order makes the math increasingly complex and unsolvable. We follow a priority rule called ILATE, ranking functions from top to bottom. In x times e to the x, the algebraic term is higher on the ladder than the exponential. This tells you exactly which term becomes u and which becomes v. ILATE provides a reliable sequence for the calculation, ensuring the problem stays manageable from start to finish. When we move to definite integrals, where the problem is bounded by specific numbers, we encounter property 4. This is one of the most frequently tested concepts in advanced exams. Property 4 shows that integrating a function from 0 to a equals integrating the function of a minus x over that interval. Visually, this is a horizontal flip. While the curve's orientation changes, the total area inside the bounds remains identical. This property allows you to rewrite an expression so that terms in the numerator and denominator can be combined and simplified before you ever calculate the area. This previous year question is a classic example. It looks difficult because of the trigonometric fraction, but the setup is a perfect candidate for property 4. When property 4 replaces the variable, the sine and cosine terms swap. Adding this new version to our original equation creates a numerator that matches the denominator, simplifying the entire integral to 1. Solving high-level problems isn't about the speed of your calculations. It's about recognizing which properties allow you to simplify the expression before the integration starts. These 3 methods cover the majority of what you will see on an exam. Look for derivative pairs, rank your functions using ILATE, and use property 4 when your bounds start at 0. Recognizing these structural patterns provides a roadmap through the most common integration challenges in the Class 12 curriculum. Identifying these cues allows you to determine the path through a problem before you even pick up your pen. Master the patterns, and the calculus follows.